my great pleasure to introduce our very special guest who is calling us from the Netherlands, World Soil Museum. Stephan Mantel is an agronomist and a soil scientist who serves as the head of the World Soil Museum at the Utrecht, the World Soil Information, and Wageningen, the Netherlands. With more than 20 years of international experience in sustainable land and natural resources management, much of it in Southeast Asia, he combines research on land degradation and conservation with public-facing work as a curator of this most extensive physical soil collections in the world. Enthusiastic educator, he coordinates the museum's educational activities and uses this very unique collection of monoliths to inspire visitors and students about the diversity of world soils and their role in sustaining life. I was very fortunate to see this collection in person and for Stephan to give me a private tour when I came there a couple of years ago. And I wanted for you to have this opportunity as well, at least to see on a distance across the Atlantic, this really beautiful monoliths and learn more about very unique collection.
Mostly here in the museum, other than I do projects, and I was very happy to meet you here, Anna, as one of the fellow soil communicators. You are one of the best examples of that. And yeah, so let me tell you a bit about the history of the museum, and then I'll take you along on a tour and tell you a bit about the soils of the world, but also some of the stories that I also told to Anna when she was here. So this museum was founded in a time in the 1960s. There was a great concern about the growing world population and the need for food. So the question was, can we continue to feed the growing world population? And UN organizations, such as the Food and Agriculture Organization in Rome and UNESCO, took up the challenge to produce a soil map of the world. That didn't exist yet. There were some efforts, but there was no harmonized soil map of the world. And of course, you need a soil map if you think about where can agriculture still expand, and where agriculture is done, where can it still grow more or produce more. So that was a big project. It took 20 years to gather all kind of national soil maps, reports, and bring that together into one unified map with a common legend. That legend was created from scratch. It borrowed concepts from the US, from Russia, from France. But ultimately, it was a new legend with, I think it started with 26 or 28 units. By now, that legend has developed into a international classification system, which is called the WRB. It has 32 units, but also they wanted to have a scientific reference for that legend. So they want to have proof of the concept and in real samples. So both samples that were analyzed, but also samples that could be shown in a museum so that people could visit and see examples of the legend of the soil map of the world from different continents, biomes, landscapes, and different land uses. So from 1966 on, when our institute was founded, we went out into the world to collect, to describe, sample, and analyze soils, and then prepare monoliths that can be shown here in the exposition and also online, because of course our collection is now also accessible online. Each profile has a high resolution image with a full description and analysis data, and often we have the American classification as well in the sheet. Yeah, so what we do here in the museum is we educate students, especially our core groups are higher education students, but we also serve the general public and also secondary primary schools. And our approach has changed over time. We do more, since about 12 years, more storytelling. So instead of saying this is the ABC, our horizon, we talk about what is the land use, the history of society, important environmental events, and then ultimately we tell it looking at the profile so you understand the formation and also how people manage to survive and thrive or maybe fail in this particular landscape given the soil conditions. So what I would like to do, I need a moment to log in again into Zoom on my phone, and then I will take you with my phone along the profiles. Now I need to, sorry, I by accident I closed the account on my phone, so I'll open it again.
It's amazing. The technologies allow us to have
Well, the first time I did it, I got a request from a school in Vietnam, and one of the children there, they were doing a topic on landscapes, and one of the children, I don't know how she or he got to know about the soil museum, but they said, I want to have a tour in the soil museum in Wageningen. And then the teacher contacted me, and then I said, okay, we can try to do that. And then I was thinking for days, how do I do it? Maybe I should have a TV and a video recorder on a pedestal. And then I was telling this at the dinner table to my children, my wife, and my son said, come on, Dad, you have a selfie stick. Why don't you do it with a selfie stick and a phone? I thought, oh, okay, thank you for that tip. So since then, I've done it a lot. I was looking at much more difficult soil museum. I will turn the camera just a moment. So this is the space of the soil museum. You see all kind of monoliths on the wall. And this here in front is the lecture where we get the lectures for a big screen. But I'll take you along the other segments of the museum. But you see all kind of different colors on the wall representing different distinct soils occurring for having formed in certain parent materials or in climates or by organisms, etc., or in particular landscape positions. But maybe we should start here, because the question is, how do we get this diversity of soils? And this is a cabinet where you see minerals. They look maybe a bit less impressive than the soils, but here are primary minerals that are on the earth crust and the earth mantle. But the minerals that you see here are all secondary minerals. So they are accumulations of different kind of minerals, salts, iron, aluminum, and they all have formed through soil forming processes. Gypsum, but also plintite and what's it called? Bauxite, so which is in the ore for aluminium. And here you see a piece of hard iron, which is from a landscape in Africa. So we cannot see soil forming processes, but so they're, because often they're very slow, they take over long periods of time, but they are extremely strong because they change whole landscapes and they invert whole landscapes, and certain minerals are lost from the landscape, others concentrate so that they become ores that we mine. So that is the basis for soil formation, and that ultimately explains this quite large variation we have in soils, in landscapes, even in fields, but certainly over continents, in biomes like rainforest, desert, coastal areas, etc. Now, let me start with showing you the soils of the Netherlands, even though you're in the US, but maybe I tell you a bit about this particular story of the Dutch, how we survived in a delta area. We have a range of soils in the Netherlands, and one of the soils that is particular for the Netherlands are swamp soils, because we are at the mouth of big rivers and in a coastal area. We're at the lowlands, so part of the Netherlands in the west is 8 meters below sea level. We have good dikes to protect us, but it means that we have high groundwater level, and then we can have organic soils. So these are histosoils. So soils mostly build up of dead plant material, which have a specific ecology, but also require a specific management. So in past times, people used to excavate these soils, and then they made peat bricks. So these are excavated parts of top of the horizon of peat, which were then dried and then burnt in stoves in houses before we had central heating. The problem with peat soils is when you drain them, the peat decomposes, and then you get land level decline. That's one problem, because the cities in the Netherlands that are built on these former peatlands, these former swamps and drained peat, they suffer from cracking houses, damaged infrastructure, etc. And also with the decomposition, CO2 escapes to the atmosphere. And of course, we want a lower CO2 budget in the atmosphere. So those are two negative sides of this manipulating the groundwater level in peatlands, and therefore we also have parts where we are re-wetting peatlands. That's because of these issues. And then the Netherlands is in the mouth of big rivers. We have let's say, reclaimed part of our country is reclaimed from the sea. So we put dikes around areas, then pump the water out. That's why windmills are a prominent, let's say, the icon for the Netherlands. Wooden shoes because of wetland, and then windmills to keep the water out of and diked areas. So we have a lot of canals and dikes to keep us safe from the water. And that has not always been so, but for the last 150 years, that was work in progress by engineers that developed or redeveloped these lands. So we have a lot of young soils, anti-soils and incepti soils in your classification. In our classification, there are arenosols, chemisols, and chemisols, arenosols, and yeah, of course, also histosols. Yeah, and then I already said that we had a big impact on our landscape, manipulating soils. And what you see around the world is that people, when they are confronted with certain soil conditions, they try to optimize their goal, like production or risk aversion, or well, there may be many different goals for managing land. And part of our landscape are Pleistocene cover sands. So they are cover sands that were deposited on the landscape in the last ice age, when the North Seabed was dry and winds were blowing material from the seabed onto the surface of the land. And this is an example of such a soil. You see, it's a sandy soil. Within the bottom, and there's ice pushed material. So this is pushed material from the ice slope, that the glacier that intruded our country in the ice age before last, and on top there are cover sands, and what developed in them was a spodic soil. So this is a spodosoil. In your American classification in WB, it's called a potsol with a spodic B. So you have here the accumulation of iron, aluminum, organic matter, which has traveled downward from the top, and therefore you have this ash gray topsoil, which is devoid of most of the minerals, and is very poor in weatheral minerals and nutrients. So therefore you see on the top, you see this organic layer. It is in an O horizon, so just undecomposed organic matter, which is not mixed with the sand because there's little biological life because of the poorness of the substrate. Now, people in the Netherlands in former times, before we had good dikes, they settled on these sandy plains to avoid flooding and to be safe from the water and not to lose your house and your crops to the action of water. But living on these poor sands, they had to do something about soil fertility. Mind you, this was before mineral fertilizer. So they had to find nutrients to fertilize the crops. So how they did that, they gathered vegetation from about 7 times the area of their field, and they also had free-ranging animals, sheep mostly, during the day, and at night they would be put in the stable. And then the vegetation was also brought into the stable, where also the manure was released by the sheep. And here you see this. Ultimately, it's a concentration of nutrients from the surrounding area on that field. And so this is how man-made soils were created. Here you see the similar soil of this one. So this is a former spodosol, but you see the first half meter of the soil is altered by humans by this long-term fertilization and bringing onto the surface manure with vegetation. And that meant people could survive on these soils. They could raise their families and they could feed their families. It was not a rich life. I mean, the people were poor and they managed to survive, but at least they could survive. So on farm level, it was a soil quality improvement, but at landscape level, it was ecological disaster because they concentrated the nutrients from the surrounding area, but also removed the vegetation, which meant that most of this sandy landscape was left bare, and wind erosion got hold of these landscapes and removed large parts of the topsoil, overblowing villages, and it was actually ecological disaster. So by royal decree of the turn of the 19th to the 20th century, this was forbidden to practice anymore. And more or less in the same time, mineral fertilizer, especially nitrogen, was introduced in agriculture. So that was balanced, that the loss of that type of farming. We have a section also humans and soil. It says here man and soil, but it's actually humans and soil. And these are all very distinctly soils influenced by humans, both the negative and positive side. These are polluted soils. This is a soil with remains of the industry that burns residue from garbage. This is the urban soil, which has the pavement on top, and then you have construction sand. And if you go down in the profile, you read the rest of the history of the soil. This is a former garbage heap. Well, Anna is specialized in urban soils, so you know much about these soils. And then here you have the original spodo soil that is below all these layers. So this is a buildup of human history where in the past, residue, let's say garbage, was introduced into the soil to get rid of it. But of course, this means pollution and then trouble for the future and for the groundwater. There are other soils which are also interesting from past era. This is a kind of mysterious soil from the Americas. This is a terra preta, which is a soil native of Brazil, from the Amazon. The original soil is among the poorest soils of the world, oxysol in your classification system. But the early discoverers, and actually the second director of ISRIC was one of the first to describe these soils scientifically. He did his PhD on the soils of the Amazon and released a book about it. But he found soils pitch black in the Amazon, overgrown with forest, but also evidence of human activity, like pottery fragments and other artifacts and they could date those artifacts from pre-Columbian Indian population. So that means before the Europeans arrived to the Americas, before Columbus came to the Americas. And these soils are in many soil pits pitch black, and that is in a way strange because we know that many of these populations, they disappeared after the Europeans arrived in the Americas because of cruel methods applied to the original population, but also diseases they brought to which the native population didn't have resistance to. So this management system stopped. Forest took over again of these landscapes, but soils are, the organic carbon in soils is an equilibrium between input and breakdown. And as long as the input is at least equal to the breakdown, it is and remains at the same level or increases. But after Columbus arrived, many of these soils were left unmanaged. But more than 500 years later, these soils are still pitch black in a tropical climate. And that is strange because you would expect that these soils would go back to their natural state, which means continued breakdown of organic matter. And that didn't happen. And that is fascinating because that means that these soils were made by these earlier populations sustainably fertile, from the poorest soils in the world to very fertile soils in the world. So that is magic. And for scientists already for decades are trying to find the key to how these soils were formed. And there's a partial answer. The people managing these lands earlier, they have introduced a lot of waste and a lot of organic material. And these soils are originally very poor in phosphate, so they introduce fish bones, turtle bones, introducing phosphate, but also charcoal. Charcoal is like clay in organic matter, has a charge, a net negative charge, which means it can bind to positive charged elements, the plant nutrients, calcium, magnesium, potassium, and interchange it with plant roots. But so now there's a medium on the market which is called biochar, which combines these elements. But still, we are not. So it's a soil amendment, soil improver, but we're still not yet able to recreate the terra preta. So this is something which is needs continued research. In Cornell, there's a long-term research going on to terra preta in Wageningen as well, in Germany as well. So yeah. We can learn something from earlier civilizations. If you look at the climate wall, so our museum is divided into the soil forming factors. So we have relief, landscape position, there we have parent material, we have a section on time and organisms, and here we have the climate wall, so the 5 soil forming factors. And if you look at the climate wall, here you see orange-red colors dominating in the humid tropics. We have the desert with white spots on the profile. And then we have the temperate areas, subtropics. There are different things going on there, from potsolization, which you already saw, clay movement in the profile. And there we have the steppes and the prairies and the pampas. and then the subarctic areas. But if you look from left to right, you will see a clear color gradation. You see that on the left, in the tropics, the colors are orange, yellow, and red. Then you get a bit of whitish spots on the profile in the hyper-arid zones. You have a mix of colors in the temperate areas of tropics. But when you go to the prairie, the grasslands of the world, and then the colder areas, you see brownification. So let's say more browner colors, which means higher organic matter in the profile. So that is interesting. It points to the domination of certain soil processes in certain climate zones. And that is the principle of zonality. There are soils which are bound to more specific climates. So in the humid tropics, we have extreme weathering. Often these are all parts of the earth crust, like parts in South America, Brazil, and in parts of Asia, especially Central Africa as well, where you find these extremely weathered soils with dominance of red and yellow colors, and that points to the dominance of oxides of iron and aluminum, hydroxides and oxides of iron and aluminum. They are relatively enriched with iron and aluminum. Why relative? Because the iron and aluminum was already there, but other components have washed out over time, over thousands, sometimes millions of years. And that means that you're left with a soil which is devoid of many elements that were originally in there in part of the earth crust, but have left the system. And so these soils are high in oxides, clay-like minerals, sesquioxides, and kaolinite. They're physically often, especially, this is an oxysol, this one is from Brazil, physically very strong, but chemically extremely poor, devoid of nutrients, almost zero charge, so almost no cation exchange capacity, so no capacity to retain nutrients even if you add them. And then they have the tendency to fix phosphate, because high content of iron creates iron or aluminum phosphates, which makes the phosphate inaccessible to plants. Now, what do we do when we manage these soils? If you have fertilizer like the Australians in tropical Queensland, they say these are fertile soils. No, they're not, but they use it as a kind of substrate for sugarcane growing, and then they add lime, they add fertilizer close to the roots, and then they produce well, of course, because these soils are physically stable. But if you have no input, then you are much more in trouble. And the original, let's say what most people do that originate from these areas, they do slash and burn, which in principle is a sustainable system. You cut vegetation on the plot and around it, you burn it, and with the burning you release nutrients, which raises the pH of the soil and also adds nutrients to the soil and make it fertile. And then you can grow crops for 2 years, and then you move plot again and leave that soil to regenerate for 20 years. So you have a cycle of 20 plots, and when you come back to the plots after 20 years, it's regenerated and you can start the cycle again. The problem is that population is growing fast and people have less and less space to move, which means that the cycle is shortened, and then therewith it becomes unsustainable. And then you have to think about intensification of the system, which is of course not so easy to do, easy to think, but not so easy to do. Another tropical soil, which is your ultisol in the US classification, in the WRB is the acrisol. It is also a tropical soil, mostly bound to the tropics, but you have this clay movement in the soil, so the RGB horizon, and which means the clay has moved from the top to the subsoil over time, but it is a poor clay with a low buffering capacity, low nutrient, low base saturation, means low nutrient containing. Acid soil, often high in aluminum. That's why you see the bigger plant roots, they concentrate in the top. They don't go down into the profile because the environment is quite aggressive in the subsoil. Yeah, what do you do if you are a farmer with low access to inputs? Yeah, then you do again slash and burn, or you adapt to the environment. And that is, of course, what people often do. You can adapt by growing acid tolerant, low nutrient demanding crops like cassava, pineapple, black pepper, rubber, those kind of things. And actually, another problem of these soils is that they are highly erodible. The top is silty because the clay has moved downward, which means the aggregate stability of the soil in the top is very low. And therefore, they are very sensitive to the impact of raindrops. and also excess of heavy machinery. So these soils easily crust, are compacted, and easily eroded. They can spectacularly erode in a matter of weeks when you leave them bare. So that's and most of the fertility is in the top because the organic matter is concentrated there. So if forest is removed in those soils, it's very important to keep them covered and to disturb the topsoil as little as possible. And yeah, in the tropics, plantation crops are often sustainable uses of these soils because they cover the soil for a longer period, which means they protect them for erosion. One important soil, I talked about the terra preta with high organic carbon, introduced by humans, but you also have soils with high organic carbon under natural formation. And this is the soil from the prairies in the US. This one is from South Africa, but it's a phaeozem. In your classification, it's a mollisol. So the soil formed under high grasslands. And you have, in WRB, we actually differentiate between 4 different types, actually 3 different types of high carbon containing grassland soils, and in different climate zones, but also in different, let's say, thickness of the A horizon. And but in American classification, they are separated in different forms of the mollisol. Well, you know the story of the Dust Bowl. I'm sure that Anna has told you that. The 1930s in the US, where there was a big economic crisis, but also actually the environmental crisis may have been bigger because the plowing of the prairies provoked wind erosion, loosening the topsoil when the roots of the plants were removed, and then creating massive wind erosion. And actually people couldn't see the sun anymore. Dust infiltrated the houses, and millions of people had to flee the area. So it provoked a mass migration out of the area of millions of people and led to extreme poverty and food problems. So that was a hard-learned lesson learned for humanity, and one of the responses was zero tillage. Zero tillage is one of the ways to conserve the structure of these soils and keep the topsoil conserved and in good state. The most extreme case of mineral soils with high organic carbon content is the beautiful soil from Russia, Ukraine, also in China, is the Chernozem. Here you see secondary carbonates, which is diagnostic for these soils. They have to have that in the subsoil, which means primary carbonates dilute with the evaporating water and then precipitate in the subsoil. But you have this extremely deep organic matter-rich topsoil. And this is a beautiful soil. I call this the champion of soil quality. It has all kinds of properties that you would like from a soil. Beautiful structure, good rootability, water holding capacity, high fertile, high organic carbon containing, very deep, and with a good fertile substrate in the subsoil. The problem is that these soils, like your mollisols in the prairies, these form under the high grass steppe of the Russia and the former satellite states, in a very particular climate, by the way, in a rather dry climate, 250 millimeters to 400 millimeters of rainfall annually, which is not a lot if you want to do agriculture. Actually, you need supplementary irrigation. I have seen Chernozems under 600 millimeters of rainfall, but it's more of an exception. But they form in a particular climate: long wet spring, short dry summer, harsh cold winter. And in the long wet spring, moles actually take the high grass steppe with a high biomass that develops on this rich substrate. And moles, you see here a beautiful mole hole, which is filled up with material from above. So the moles take biomass down into the profile, and also topsoil material falls into the lower part of the profile as an organic matter pump. And here you see a picture of a profile, maybe it's not well visible, with all kind of crotovinas, they are called, so mole holes, which acts like an organic matter pump. And then in the summer it stops, and in the winter it also stops. The organic matter doesn't break down because of cold conditions, and then in the spring the organic matter pump starts running again, and that creates these beautiful, very deep organic matter profiles. Now people also started to ultimately plow into these soils when population expanded, and that led also to problems with erosion. Actually, the Chernozem soils among the most beautiful soils of the world. They are degrading worldwide wherever agriculture is practiced. And it's not that you cannot do agriculture on them, but you have to be conserving the topsoil. So using perennial crops, cover crops, etc. So you need smart management. And maybe low till or no till or direct seeding. So that's the let's say the management challenge to do that. You also have other soils with clay movement, but then with rich clays, not the tropical clays. These are the alphy soils or the Louvy soils in WRB classification. And look at this beautiful subsoil structure. It is beautiful angularly blocky structure, and that means this subsoil is rich in clay, so it can store water within the clay lattices, but also in the macroporosity. So in all these voids, which you see here, water can be stored, and also nutrients on the surface of the clay. So that means in a big drier period, the subsoil acts as a water buffer for plants that go into these soils. And also they are high nutrient containing, high buffering. So beautiful soils, but again, also with the algae soil, the topsoil is more silty. So you have to be very careful for compaction, crusting, but also especially erosion. There are different types of soils. In USDA soil taxonomy, you call them arid soils, so soils from arid areas. And in WRB, they are separated by the type of salt they contain. So, and then in the American classification, you get that into the longer names specified. This is a calci soil with secondary carbonates which travel upwards with a bit of water that comes into the soil and then evaporates, and then you get calcium carbonate dominated soils, which we call calci soils. There are soils which are used a lot for agriculture in the Mediterranean area, so countries like Italy, Spain, Turkey, and they grow mostly wheat on them, wheat varieties. You also have soils with calcium sulfate, so gypsum. You may see some gypsum crystals. So the same process with evaporating water, depending on the parent material. Gypsum travels upward, dilutes, but then precipitates again in part of the profile. And also these soils are used for agriculture. Not very easy to manage, but they can produce. And then you have other soils that can accumulate in the soil, like this salt pan. This is a salt from the Turpan Desert in China, where salts travel upward in the profile, but when the water escapes to the atmosphere, the salts remain, and then this thick crust develops, and ultimately over time the crust will grow on the lower part and maybe even harden. So that's a petrosalic soil, which means it is a high salinity, high sodium chloride. And that is bad news, of course, because that reduces the capacity of plants to take up water from the soil. So these are very poor soils. And there are also soils with exclusively sodium on the complex, so sodium saturation. And sodium saturates the clay complex. That means it destroys the structure because it affects the aggregation of clay particles. And here you see there's almost no structure. And then it precipitates again in the subsoil where you have these heavy typical structures of the natric D. So very difficult soils for people that want to do agriculture on them. So these are the zonal soils. And then you have soils which are non-zonal that occur in all kinds of different landscapes and also, specific parts of the landscape, but in different climate zones over different continents. For instance, soils on the riverbeds, soils with stratification, which means you see the lines of the river deposition of different layers of sand, silt, and clay that have been deposited in different regimes of overflowing of the river. Those are fluvial soils. I think your soils are anti-soils and steppe soils, I guess. I haven't used the American system for a long time. And then you have the soils that have a big influence of groundwater. So groundwater is almost at the surface. And then you have just loose clay particles, no structure formation because there's no oxygen, no soil life that can glue particles together to form structure. Only in the top, where there's excess of oxygen, biological life can glue particles together and create structure. And in the Netherlands, we have drained most of these soils so that we manipulate the groundwater. So let's say to lower it to 0.5 meter so that farming can be done or grasslands. So the color is grayish. That is because iron is reduced, it's in F2 plus. So there's and when the iron oxidizes under influence of oxygen, for instance, if roots penetrate the system, then you get these reddish colors where iron changes form. We also have very well where we see the senile soils, so the oldest soils in the world on the left of the climate wall. You also have the other spectrum of time influence in soils. For instance, these are soils which are newly deposited from eroded hill slope, and then new fresh materials deposited on the low part of the hill slope. So then soil formation has to start again. Or, for instance, soils from a volcanic eruption. This is just volcanic ashes, and then soil formation really has to start from zero there and form horizons, and you have influence of biota, etc. The dominant soil in the world are leptosols, so the shallow soil forms in the world, and I think in your question there are inceptisols. So shallow soils, because they are on slopes and formed soil move downward in the slope, and you always keep a shallow soil. This one is from Jordan, where you see only 10 centimeters of soil, and then below that you have the bare rock. And this is another example where you have just degrading slate, and here you have a few centimeters of soil forming in this degrading rock. So this is what we call the baby in the collection. It's just very early soil formation. So we have, maybe 2 more soils, 3 more soils, and then I'll give you space for questions. But these are vertisols. You have them. You have extensive areas of vertisols as well in the US, which are high clay-containing soils, and also the rich active clay that can shrink and swell. So monolithic clay, 2-to-1 clays that can take up a lot of water in their interlaces and then swell. And in the dry season, they shrink. So you get deep cracks into the profile, often up to 1 meter with a very wide crack, and they form slickensides. So these are these pressure phases of soil material moving over each other because the pressure builds up and finds its way upward. And therefore, you have this micro topography, Gilgay, they call it, on these soils. Very difficult to manage. They're chemically very rich. They have high buffering capacity, high nutrient containing, fertile soils, but physically extremely difficult to work. And you have a very short access time with machinery. And in the wet season, it's too sticky to access. In the dry season, it's too hard to work. So yeah, and also plant roots suffer from the moving of this clay, which creates tension in the roots. But the optimal use of these soils, except from cotton in certain areas, is rice cultivation. Because if you saturate these soils, if you inundate it with water, they close completely, which means the water that you put on the land for the rice to grow in doesn't escape to the deeper layers. And in parts of Africa, they use these type of soils because they also are mostly located in plain lands, in valley floors. So that is ideal for rice cultivation. Well, here you see 3 soils. Those are all formed of volcanic ashes. A soil from Indonesia, a soil from Ecuador, and a soil from Iceland. And the Iceland soil is a good example of how we do storytelling in the museum. Iceland is a very cold and volcanic island. It's the collision between the American and the European plate. It's full of volcanism, and it's cold and wet. So what you get there, in most areas, it's either completely volcanic or completely organic, histosol, but often a combination of those. So here you see pit formation, and then you see an ash layer from the Hekla volcano. On the other side, this profile from the north side of Iceland. This ash layer comes from a volcano from the north side of the island, the Hekla volcano, and it erupted 3,000 years ago. And then peat formed again, and then there was another eruption also from the southern part of Iceland, the Laki volcano, which is a break in the earth crust of 25 kilometers long, and that volcano erupted 4 months continuously. And then you get peat formation again. Now, this Laki ash layers bear witness to a very important period in Iceland. The eruption was huge. It brought a lot of dust into the atmosphere. It was a dramatic event for Iceland because half of the livestock died because of fluoride intoxication, and also a quarter of the population died. That's why they say Iceland is the land without songs. But also worldwide, the climate was changed. 10 years, 1 degree lower temperature on Earth because of the ashes in the atmosphere reflecting solar radiation, and in Iceland even 5 degrees lower of temperature for 10 years. So that was a big impact, and that also had implications for food productivity. For instance, in India, misharvest in India, in the Nile Delta, but also in continental Europe, France. And 1783 was when the Laki erupted. It's very close to an important period in Europe, 1786 to 1789, the French Revolution. And they say that the Laki eruption was one of the sparks for the French Revolution. Not the cause. People already said dissatisfied with the king. There were big differences in society. There was poverty. There was food shortage. But the Laki eruption aggravated the food security situation. And, well, therefore, the link between environmental processes, the soil that bears witness to it, and very important societal processes. And if you look at they say volcanic soils are fertile. In many tropical countries, people go very high up the slope of volcanoes, which is in principle dangerous because volcanoes are unpredictable. But they do that because, one, volcanic soils are often fertile because they bring weatheral minerals into the landscape, rejuvenating soils. But also because if you go higher up in the tropics, it gets cooler, which means you can grow other crops that you cannot grow in the lowlands. So, for instance, strawberries or potatoes in the tropical climate, but you're higher up on the slopes of the volcano. Now, if you look at this soil, this is a volcanic soil from Indonesia, from Ecuador and Iceland, as I told you. And in Indonesia, people thrive on these soils because they can do 3 harvests of rice. But you see also a population. Actually, the soils explain the population distribution in Indonesia. You have the non-volcanic islands like Borneo, which are lowly populated, mostly on the rainforest, although now oil palm is expanding into the forest. But let's say if you go thousands of years back, you can trace a long history and culture development in islands of Java and Bali, which have volcanoes which are basic and lead to fertile soils and allowing 3 harvests of rice, while in the other islands, population development was quite much lower. And that means, so in fact, if you plot the population density on the soil map of Indonesia and the geological map, you see a very direct relation. And in fact, if you do that for the world, where the Lust Belt is, the fertile, let's say, the river plains, you actually also see a relation. So there is a good relation between early population development and soils and landscapes. Okay, maybe the last one I will show you before I give you the floor. One soil that you also have in the US are these soils which have beautiful coloring, but it is bad news. You see these yellow spots, which is jarosite, components of sulfur, iron, and then a reduced soil. These are acid sulfate soils, so in WRB trionic soils. So they occur in soils with marine deposits, and these marine sediments, they often carry also components of pyrite. And pyrite is a sulfur-containing sediment. And if these soils are underwater, so in the Netherlands we are in a delta environment, so typical marine sediments, then they have a pH of 7, more or less neutral. But when you drain them, and we did that a lot in the Netherlands by empoldering and let's say regaining land from the sea, then farmers were given plots of specific areas, but some farmer families were poor off because their crops wouldn't grow, even grass wouldn't grow. And they were on these cat clays. That means after drainage, then these soils acidified because the pyrite, in combination with organic matter and microbes, then converts to hydrosulfuric acid. So if you put your finger in acid sulfate soil, you burn your finger because the pH dropped from 7 to below 3 even, and so much more acid than vinegar. So very, very difficult to manage these soils. Think about the Nile, the Mekong Delta, for instance. They also have a lot of acid sulfate soils, and what do you do then? There's not much to do. You can lime, grow on mounds or let's say to flush the acids out, and be patient, I think, and also use acid tolerant crops. We have the ISRIC has a lot of information online available. We have this is the central table, but for instance, we have the SoilGrids system. If you want to know for any area in the world soil properties at a resolution of 250, let's say the smallest cell sizes are 250 by 250 meter, and you can look at properties such as soil classes, but also chemical soil properties or physical, and look at the clay content map of the world for standardized depths, and then you can see, for instance, US, where is more or less clay in what content, and if you click on the cell, you get the estimate of that clay content for a specific depth. So that's the SoilGrids system, and on our web portals, we have also access to other databases on soils. It's all open source, so if you need soil information for your study, your project, or your future work, then of course, the US has good data holdings on US soils, but if you look for other areas in the world, then you may find it on our website.